Well, what do you know? We're back. Means it's the next lesson, so that means we're going to get into RAID controllers. All right, let's get started. So RAID is obviously an acronym, but it stands for Redundant Array of Independent Disks, right? So a RAID system could be hardware or software and virtualizes physical storage drives to improve performance and create data redundancy. All right. Controller-based RAID generally refers to hardware-based RAID as opposed to server-based RAID, which is both software-defined and software-hardware hybrids. So what are we talking about when we say RAID controller? Well, it's a card or a chip located between the operating system and the storage drives, usually hard disk drives. So RAID provides data redundancy as well as or improves hard disk drive performance. Most RAID levels do both. RAID does provide redundancy on SSDs, but does not improve SSD performance. Okay, so RAID manufactured specifically for SSDs will provide both redundancy and improved performance. Follow? Now, RAID controllers work by virtualizing the drives into distinct groups with specific data protection and redundancy characteristics. The front-end interface communicates with the server, usually via a host adapter. That's HBA, host-based adapter, right? And the back-end communicates with and manages the underlying storage media, usually ATA, SCSI, SATA, SAS, or a fiber channel. RAID controllers are classified by multiple characteristics including drive types, such as SATA or SAS, the number of ports, and the number of drives it can support. Now, specific RAID levels as well, interface architecture, and how much memory exists in the native cache. So for an example, it means that a controller manufactured for a SATA environment will not work on a SAS array, and that a RAID 1 controller cannot be modified into a RAID 1.0 or RAID 10. RAID controllers are not storage controllers. Okay? Storage controllers present active disks to the OS, while the RAID controller acts as a RAM cache and provides the RAID functionality. The number and identity of RAID disks depends on a RAID controller's configuration. All right, so now we got all that out of the way. We got to talk about the dedicated hardware controllers because they come in two different architectures, an external RAID controller card and an internal RAID on chip. Let's have a look at the RAID controller card, which is a plug-in expansion card that connects to a PCIe or PCIX motherboard slot. Right? It contains a RAID processor and I/O processors with drive interfaces. Now, the less expensive RAID on chip is a single motherboard chip that integrates the host interface, HDD/I/O interfaces, the RAID processor, and a memory controller. The firmware starts up RAID during boot up, then transfers control to the drivers. So let's talk about software RAID delivering RAID services from the host. And this is going to come in two different flavors. Software-defined hosted in the OS and a hybrid architecture that contains a hardware component to relieve the load on the CPU. The software-only RAID is usually included as a native function within the OS, which makes it the least expensive of the RAID options. The host-based application manages RAID calculations and attaches to the storage drives using an HBA or native I/O interface. It starts up when the OS loads the RAID driver. With a hybrid hardware-software RAID, this is going to use a hardware component to deliver RAID BIOS functions from the motherboard or HBA. But the hybrid technology adds another layer, and it's going to be more expensive than the software only. But it protects the RAID system from boot errors should something happen to the operating system. So why don't we have a look at different RAID levels? we're going to go in pretty deep. You ready? I'll give you a summary. RAID controllers are specific to different RAID levels. Now, the most common levels are RAID 0, 1, 5, 6, and 10 or 10. For more in-depth information, let's have a look at each level individually. RAID 0 is often called striping. RAID 0 is the only RAID level that does not provide redundancy, but it increases hard disk performance. So RAID 0 will split files and stripes the data across 2 disks or more, treating the striped disks as a single partition. Since it treats multiple disks as a single partition, if even one drive fails, the striped file is unreadable. What's a usage case? HDD performance improvement only. There's no data redundancy. I repeat, there's no data redundancy, and there's no data redundancy. Not to be redundant, but there's no data redundancy. RAID 1, mirroring. So RAID 1 works on 2 or more disks to provide data redundancy and failover. So it reads and writes the exact same data to each disk. So that means, should a mirror disk fail, the file exists in its entirety on the functioning disk. Now, when the failed disk is repaired or replaced, the RAID system will automatically mirror data back to the replacement drive. So RAID 1 also increases read performance, and a good usage case here would be data redundancy and faster reads at a low cost. So what's this RAID 5.6? Well, striping with parity or double parity. So RAID 5.6 combines the performance of RAID 0 with the redundancy of RAID 1, but requires about 1/3 of the usable capacity. So parity just refers to raw binary data. RAID 5 stripes data across 2 or more disks and calculates block-level values to create a parity block. RAID 5 stores dedicated parity blocks on striped HDDs. Now, should a drive fail, RAID 5 uses its dedicated parity block to rebuild data on the remaining nodes. RAID 6 operates like RAID 5, but requires a minimum of 4 disks in an array. So it can store an additional parity block on each HDD. This results in a highly available configuration where 2 disks may fail before the array becomes unavailable. A good usage case would be web servers, intensive read environments, application servers, large storage arrays. You know what we're talking about. All right, RAID 10, striping and mirroring. RAID 10 is going to be the most expensive of the RAID levels. It stripes across at least 4 disks for higher performance. It also mirrors for redundancy. So if we're talking about a 4-drive array, the system stripes data to 2 of the disks. The remaining 2 disks mirror the striped disks, each one storing half the data, right? A good usage case for that would be high security and high performance environments such as intensive transactional databases storing sensitive information. But RAID 10 is, like I say, going to be the most expensive RAID level for HDDs. But obviously it offers high read and write speeds as well as strong data redundancy. So RAID is a fundamental data protection and driver for HDD and SSD, as well as a performance driver for HDD. Some of the top benefits would certainly include better reliability, except for RAID 0, but RAID ensures that a single crashed node will not take an array down with it. Applications continue to operate on remaining nodes while the failed node is repaired or replaced, which maintains data consistency and guards against data loss. Data redundancy. RAID mirroring and/or striping with parity spreads data across multiple nodes, ensuring that no data is lost should a node fail. We mentioned higher HDD performance, but most RAID levels improve throughput by allowing applications to simultaneously read and write data from multiple drives. Now, this is not an automatic improvement, right? Higher RAID levels, especially RAID 10, take up system overhead, making them unsuitable for low or mid-performance arrays. These arrays benefit most from RAID, right? Performance improvement, or RAID 5.6 for performance plus redundancy. On a high-performance array, RAID 10 increases performance and provides redundancy and high availability. So the controller architecture of hardware-based RAID is going to be more expensive than software-based RAID, but it increases system performance and it's not subject to any boot errors. Cache memory. Controller-based RAID usually provides additional disk cache memory, which accelerates RAID operations. Dedicated processing. A controller-based system will independently manage the RAID configuration apart from the OS. And since the RAID controller does not require disk processing power, capacity and speed win out over software-only RAID. We talked about a lack of boot errors, and since software-only RAID is located in the OS, it's subject to boot errors that can compromise an entire array. Boot errors will not affect RAID controllers. Now, not every environment makes sense for controller-based RAID, right? In a tightly budgeted storage environment, software-only RAID 0 will improve HDD performance, and software-only RAID 1 will provide acceptable data redundancy. However, in higher performance environments with compute-intensive arrays, hardware RAID 5.6 will provide better performance than software-defined RAID. And if you need to scale up to RAID 10, you're probably going to not find any software-based alternatives that are as reliable. Well, what do you know, folks? That's it up until now. That's all about RAID controllers that you need to know. Go back and polish up some of your skills. I know you got a few new interesting facts, but stay tuned for next time. See you then.